In this video, we'll talk about section 11.1, and we're going to start our deeper look into differential equations. We've talked about these a little bit in the past, but we're going to go a lot deeper in the next few days. So remember, a differential equation, which we will oftentimes abbreviate as a DE, is an equation with at least one derivative. So some examples are y double prime minus y equals 0, dy dx equals xy quantity squared, and y prime plus 2y is equal to 0. So one way of classifying differential equations is by their order, which means the highest derivative that appears. So the first differential equation is a second order differential equation, and the second one is a first order, and so also is the third one a first order differential equation. In the green, you can see another way of identifying or classifying differential equations is separable differential equations are those that can be written in the form where all of the stuff with y's can be multiplied by dy and separated from all of the stuff with x's multiplying the dx's. In AP Calculus, all of the differential equations that we solve are what are known as separable differential equations. And to solve other kinds of differential equations, you have to learn other techniques that we aren't going to talk about in AP Calculus. A solution to a differential equation is a function. It's a differentiable function on an open interval that contains the initial x value and that satisfies the equation, the differential equation, when the function and its derivatives are substituted in. So remember, when we solve a differential equation, we're looking for a function. The general solution shows all of the solutions to a differential equation, so they'll oftentimes have a constant and sometimes more than one constant. A particular solution satisfies the differential equation and the initial conditions. So for example, so now we're not solving any yet, but we will soon. So can we show that c1 cosine x plus c2 sine x is a solution to the differential equation y double prime plus y is equal to 0. So in order to plug in everything into this differential equation, we need to know what is the second derivative. So we'll start by finding the first derivative. So remember, c1 and c2 are constants, and the subscripts means they may be different constants. So the derivative of cosine is negative sine, so that's going to be a negative c1 sine of x, and the derivative of sine is cosine, so that'll be a plus c2 cosine x. So there's our first derivative, and then we'll differentiate that to get our second derivative. So a constant times sine x, its derivative is going to be that same constant, and then we get to a cosine x, and the derivative of cosine is again negative, so that's going to make that a minus c2 cosine of x. So here's our second derivative, and we're going to now plug it into our differential equation. So we're going to get y double prime, that's the negative c1 cosine x minus c2 cosine, did I do that right? I don't think that's right. So let me back up. Our first derivative had a cosine, so our second derivative, that should be a sine. Sorry about that. So that should be then a negative c1 cosine x minus c2 sine of x. There's our second derivative, plus our original function, which was c1 cosine x, and a plus c2 sine of x, and we're hoping that's going to be equal to 0, and sure enough, you can see that those are going to cancel each other, and likewise those will cancel each other, and it is going to in fact make this equal. Okay, and that's what it means to be a solution. So we haven't solved anything yet, we're just at this point trying to verify solutions. So here's another version. We have 3x squared plus 2y squared is equal to c is our solution. We're going to try to show it's a solution to 3x plus 2y prime, and then after we do that, we're going to try to solve for the constant. So we're going to plug in here. So we need to know first what is y prime. So I think we can do this easier just by using implicit differentiation. So if we differentiate our function here, that's going to be a 6x. That's going to be plus 4y prime using our implicit differentiation skills. The derivative of the constant c is 0. We're going to need to solve for y prime. So we can subtract that 6x to the other side, and then solving for y prime, we'll get a negative 6x over 4y. We should probably reduce that and call that negative 3x over 2y. Now we're going to go to our differential equation, and so we're going to go 3x, that's just 3x, plus 2y, I'm going to just leave it as 2y, times our y prime, which is a negative 3x over 2y, and hopefully we can get this to be equal to 1. So we can see, or to 0, sorry, otherwise we're going to be in trouble there. So we can see that the two y's will cancel, and that leaves us with 3x minus 3x, which is indeed equal to 0. So that's part A. Part B, we're going to find the particular solution. So now we are going to plug in 3 for y, 1 for x, and solve for the c. So that's going to be 3 times 1 squared plus 2 times 3 squared, and that's going to equal c. So that's going to be 3 plus 3 squared is 9, times 2 is 18. So it looks like c is 21, and that makes our equation 3x squared plus 2y squared is equal to 21. Now generally what you're going to be expected to do is to solve for y on these. So if we do that, we're going to have to do a little work here. We can subtract that 3x squared to the other side. We can divide by the 2, and so I'm just going to write that as a big fraction. And then we're going to have to square root both sides. Here's where it gets a little more interesting. So when you solve, when you square root both sides in solving an equation, you want all possible solutions, which means initially we can get either a positive or a negative. Now, we can't keep both of those because that's not going to be a function. Because then remember, when you plug in a value of x, you can get only one value of y. So that means we're going to have to decide, do we keep the positive or keep the negative? And the way we determine that is to look at our initial condition, which had a positive value for y. So that means it's not going to be the negative part, and so I'm going to erase that, and the positive or non-negative square root of all that is going to be our solution to that differential equation. So let's see what we've got. Here's another one. We're going to again first show that this y equals c1 sine 3x plus c2 cosine 3x is a solution to y double prime plus 9y equals 0. And then we're going to try to solve for the constants c1 and c2 using the initial conditions. So our differential equation needs a y double prime. So first y prime, and again we're going to take the derivative of sine. So we're going to get c1 cosine 3x, and then times the derivative of 3x is 3. And we've got c2, the derivative of cosine is a negative sine, and we'll also get a 3 from the chain rule derivative. That's our y prime. Then our y double prime, we're going to get, again, the derivative of cosine is a negative, and we'll get a sine of 3x, and we'll get another times 3, so that'll become a minus 9, c1 sine of 3x. And then we'll get the derivative of sine is going to be a cosine. We'll get another 3, so that'll be a minus 9 c2 cosine of 3x. So there's our y double prime. So we're going to try to show that it satisfies that differential equation. So we've got negative 9 c1 sine 3x minus 9 c2 cosine 3x, and then we get a plus 9 times our original function, which is that c1 sine, I don't know why that got so small, c1 sine 3x and a plus c2 cosine 3x, and we are hoping that that's going to be 0. So if we distribute that, I think we can see where we're going. If we distribute, let's see, that's a minus 9c2 cosine 3x. Distributing the 9 will make that a plus 9 c1 sine 3x and a plus 9 c sub 2 cosine of 3x. And I think we can see that the negative 9 c1 3 sine 3x will cancel the positive 1, and the negative 9 c2 cosine 3x will cancel that, and sure enough we get 0 over 0. So it is a solution. Now we are going to go further and try to find out what c1 and c2 are using our initial conditions. The first one uses y, so plugging it into our original function, we're going to get 2 is equal to c1 sine of, that's going to be 3 times pi over 6 plus c2 cosine of 3 times pi over 6. And so 3 times pi over 6, that cancels, that's pi over 2. So that means we have c1 sine of 3 pi over 2 plus c2 cosine of 3 pi over 2. That's convenient because the sine of 3 pi over 2 is 1 and the cosine of 3 pi over 2 is 0. So we're going to get 2 is equal to c1 times 1, and so there is our c1. We can use our second initial condition and use that with y prime. So we're going to get 1 is equal to 3c1 sine of, and here we are with the pi over 6 again. So that is again going to be 3 pi over 2. I said 3 pi over 2. Hold on there, that's not right, but it's not going to change anything, because actually that would have been a negative 1. But sine of pi over 2 is positive 1, and cosine of pi over 2 is 0. So I had the right answer, but I didn't do it the right way. So here, I'll try to do it right from the beginning. Since the pi over 6 times 3 is going to be pi over 2, and we've got a minus 3 c sub 2, and that, and I'm not using my y prime right, struggling on all fronts here. That's going to be a cosine, and that's minus 3 c sub 2 sine of pi over 2. And since cosine pi over 2 is 0, that's going to drop out. And since sine of pi over 2 is 1, we'll get a negative 3c sub 2. So that means c sub 2 is a negative 1/3. So then we've got to put that together and get our final answer, which is our function. So we're coming back up to our original and say it's y equals c sub 1, we are now deciding is 2 sine of 3x, and then it's a minus 1/3 cosine of 3x, and that solves our differential equation and satisfies our initial conditions. I think that's all we got for now, but we'll be doing more on these differential equations in the days that come.